my pleasure to welcome Dr. Ingo Scholtes, who is a senior assistant and lecturer at the chair of systems design at ETH Zurich. He has a background in computer science and mathematics. He obtained his doctorate degree from the University of Trier, Germany, at CERN. So he was at CERN. That's interesting. Cool. I'll talk to you about that. He designed a large-scale data distribution system which is used to monitor particle collision data from the ATLAS detector. His research integrates both applied and theoretical aspects of data mining and network science with applications in information systems, software engineering, and social sciences. In 2014, he was awarded a junior fellowship of the German Informatics Society. In 2016, he held an interim professorship at the Karlsruhe Institute of Technology in Germany. He's the founding chair of the Computational Social Science Working Group and a member of the Data Science Task Force of the German Informatics Society. His current research interests focus on limitations of network analytic methods in complex data and how to overcome them by means of model selection and higher order modeling techniques. And if you guys stay until the end of this talk, we're going to have coffee and cookies on the top floor kitchen. Thank you, please.
Thank you very much, Tina, for a very kind introduction. I think I will quit science as soon as the biography is longer than the talk. I have 45 minutes left. Okay, so thanks a lot for the invitation. It's a real pleasure and also an honor to speak to you today. What I want to talk about is about optimal models of complex systems. And, well, the provocative subtitle is why I think that we, in many cases, need to move from network models to what I call multi-model models. And I will explain on the way what I mean by that. So first, a few words actually on where I come from and what we are doing. So this is the chair of systems design at ETH Zurich. So here at Zurich is the Federal University of Switzerland. We're a group of about 15 interdisciplinary researchers, pretty much like here, so from backgrounds in computer science, physics, math, and also some social sciences. So what we are usually doing is we are engaging in data-driven modeling of all kinds of complex systems. So here's a couple of examples that I'm not going into detail, but you see that it covers engineered systems like communication networks, software architectures, or transportation systems, but also problems in social sciences, for instance, team science, social influence in scientific processes, in software engineering processes, and also some problems that have relations to life sciences and physics. So obviously what these things have in common is that they are examples of complex systems that consist of many interacting elements. And it's actually quite reasonable if we have data on these interactions to model them as complex networks. I think I don't have to tell you specifically that this is a great basis for data-driven modeling. And it's also an increasingly important foundation for data mining and machine learning that widely used across disciplines. So I'm not going to talk about the many benefits that this perspective has. So most of the work that I've done in the last 7 years actually are based on this perspective. I'm a real fan. But what I want to talk about today is actually the limitations that we see when actually we have complex data that we want to model. Because what we should consider is that in most cases where we have data on these complex systems, we are not given a blueprint of the system where we know exactly which element is related to whom and how. But what we have is we have big data, and we have to decide whether a network model is a good model for the system in question. So this has different aspects. For instance, there could be noise in the data, so that the network model is actually overfitting what we see in the data. Or in other cases, we have rich data, for instance, time series information, multi-layer information, and so on and so forth. We're casting this into a simple network topology that discards information, and that's actually an important problem that we should address. And it's getting more and more important as we have richer and noisier data on these systems. So I think this brings about some research questions that we haven't, I think, addressed satisfactorily so far. The first one is actually a simple question. Given that we have data on a complex system, when is a network model of the system actually justified? It's a simple question, but it's actually quite hard to answer in practice. And specifically what I would like to do, I would not like to leave this decision actually to a human. So what we would like to do is we would like to use machine learning and model selection techniques to kind of automatically make this decision and maybe actually also learn a better optimal model if we find that a network model is not justified. So that's basically what my talk today will be about. So I have actually two blocks. The first block is just a single slide, and that's just a teaser of something that we have done recently, and it's really just a stuff for you actually to plug in. So I just want to present what we are interested in, and if you think that's actually relevant for you, then just feel free to talk to me actually while I'm here this week. So the point is that in many cases, what we are doing is we are inferring network models from high-dimensional sensor data where we don't actually know the direct interactions that we want to model. Right? A good example are, for instance, all kinds of fMRI data, like brain networks, right? We need to infer from some kind of activities in certain brain regions, or maybe more down to earth, actually for us in the computational social science domain, we often try to infer the social network from some sensor data that, for instance, capture proximities over time. To think about the social patterns data or the reality mining project here in MIT. So what they have done is they have smartphone sensors or sensor batches that record proximities over time, and then the question is, given these data, what is actually the social network? So these data usually come in a form that allows us to cast this into some kind of co-location or co-occurrence matrix, or more general, some kind of cross-correlations, right? So it means here we have actually students in the rows and the columns, and actually the colors tell how often they have been observed at the same location around the same time. So that's the data that we get from these data. This is actually a real example. These are, I think, 96 students from the reality mining projects. So now, how do we infer a network from that? There's a couple of ways to do this, and a lot of ways, for instance, the network inference, they are based on some kind of thresholding, based on the distribution of the weights and so on and so forth. And what we could do then is we could infer such a network model. But I would argue this is a rather naive approach, because it does not account for many characteristics of the data, and it also doesn't account for the fundamental combinatorial problem of the combinatorial nature of the problem. For instance, certain students have actually very different activity levels. Maybe they are showing up in certain places more often than others. And based on that, we have different expectations for certain pairs of students to meet each other, which we should take into account when we want to answer the question whether there's a significant link between two students, right? Also, the total number of observations, the observation period, is important to consider. So the way we actually address this in a recent manuscript and in the subsequent application is by means of a statistical ensemble approach. So we call this generalized hypergeometric ensembles. And the benefit is that it's an analytically tractable statistical ensemble that generates probability spaces of directed multi-edge networks that are useful whenever you have repeated interaction data from which you want to infer significant overrepresented interaction space. So in this concrete example, what we could do, this is now just a visual illustration I leave out of the math, you can talk to me later. What we can do is, based on the activity levels of the students and the total number of observations of co-locations, what we can do is we can infer analytically dyadic probability distributions for the encounters between any pair of students. And you see that this is actually highly heterogeneous because the activities of students are highly heterogeneous. Once we have these probability distributions, we can actually check the actual co-location observations that we have, and we can use p-value to identify non-significant events, and that is basically giving us a low-pass filter for the co-location matrix, which we can use to denoise the adjacency matrix. And then actually from this we can construct a better inferred network model. And that is actually the actual social network that we get for the reality mining data set. So you see that it's actually completely different than the simple thresholding network before. And what we could show actually in this paper is that we can, with this, for instance, with the community detection, better infer, for instance, real research lab memberships of students that are completely disguised by noise if you use standard thresholding. So that's one application of this. But since this is a framework where we can make analytical statements about probability distributions and also likelihoods of models, what is nice is that we can also use it for model selection. So what we can do is we can compare different models by tuning the null models that we use for the inference, by putting in different hypotheses about the origin of our interactions. So for instance, we could test whether the mean fit model is enough to explain the observed interactions, or whether there's some latent space, improved model, or whether we really need the network model, which is actually in this line here the most complex one because it has dyadic information actually. So in this example, what we would find, for instance, if we replace groups of students simply by their research labs, and then actually we make a mean fit model of these research labs, actually this is enough. It's a very simple model, and it's enough to explain the actual interactions that we see. It's actually quite easy to understand this because that's what drives the co-location. So maybe there is actually no friendship network in the data. It's actually very simple to explain, and we can test these different hypotheses and weight them against each other. So I like this framework because it has some nice perspectives in terms of not only topology inference, but also in terms of model order reduction. So we see that in this case, we will find that we probably oversampled the problem, right, the phenomenon. And we can also do anomaly detection because obviously then if there's some links absent in this model, it actually may signify something interesting. So as I said, that's concluding actually just this teaser about this work. If you have data where you think, well, that's actually quite related and this could be useful for my case, you just talk to me and we can have a discussion on that. Yes?
I have a question. So you were saying, so I have the sensor data, and then what you do is you find the probability of two people having a link to each other. How do you do that specifically?
So it's a hypergeometric distribution that we use, which is actually accounting for the total number of interactions and also the in and out degree weights in these directed edges. So that's what we use as an ensemble constraint. From this we can derive this distribution. And what I think is the actual contribution is that we can tune these probabilities in arbitrary ways by putting in what we call a propensity matrix. So that means we can now, it's kind of an Earn model. So we are drawing links from the space of all possible links while considering these constraints. And now what we can do is we can make certain links more or less likely based on a null hypothesis that we can put in. So it's a matrix where, for instance, we put in that Tina and Ingo are more likely to interact by a certain factor above the baseline because we have some additional knowledge about the system. Then what we get is actually a complicated distribution. It's the non-central bilinear distribution. And the benefit is that even though the ensemble model is actually quite complicated because it has all of these constraints, plus these arbitrary propensities that we can put in, because of the specific distribution, we can still make analytical statements. So that's the basic idea.
And how do you get the propensity scores?
So for that actually is related to the model. So if we just want topology inference, then we would say we have equal propensities. We have no reason to believe why Tina and Ingo would be more likely to interact, right? And then we get the inferred network based on that in the method that I showed. But what we could do is now we could actually put in something like a stochastic block model. And we could say, well, there are certain research labs, for instance, that I know. And I know that people within the same research lab have a higher chance of interacting or being co-located. So I can put this in. And now I can test, well, how well does this model explain the data compared to the model where I have no propensities? And then I can see whether this is enough. So that means whether a network is needed. So it's a fairly general framework because everything that you can encode in these kind of dyadic propensities, you can cast into model selection, hypothesis testing. And group structures and latent spaces are just two examples. Right? Yeah.
So you mentioned in so finding that distribution, you said that you are looking at the in and out.
Yeah. So what we
have
are
a direction.
We can. So in the co-location data, we can drop this. So that's actually a simpler case than what we can consider. But in other cases where we have direct interaction, we can include this as well. So that's why it's actually fairly general. So what we preserve is the in and out degree sequence of the nodes, plus the total number of interactions observed. That generates our ensemble. And in this specific case, we have in and out degree being the same. We don't need this feature basically in this example. Right. Okay, second challenge, and this will keep you busy until the end of our talk. And you will not be surprised that I talk about this if you have seen any talk from me for the last 4 years. It's time series data. Because for many systems that we model as networks, these days we not only know who's interacting with whom, who's related to whom, but also when and in which order actually these interactions or relations occur in the data. Because we have more and more time series and timestamp data. So there's examples for this and where systems actually have dynamic topologies, and we can also trace these dynamic topologies in data. Think about dream regulatory networks, social interaction data, or even transportation networks where there is a topology that is kind of static, but the way actually in which, for instance, stations in the train network are connected is obviously in specific sequences based on the schedule of the trains, and that's something that we can put into the model of the system. So many of these cases we can actually represent by what we call time-unfolded graphs, or actually direct and acyclic graphs, in which we basically have a set of nodes and actually we trace them through time flowing from top to bottom. So that means here these are the first 3 steps of observation that actually we build the system over time, and so on and so forth. So this gives us a sequence of interactions between nodes. And you see this is a specific notation where we actually connect adjacent temporal copies, because that allows us actually to trace the path in the system while it is done with basically a cyclic graph representation. That's actually what we use just for our own realization purposes, but it's not really needed. So how do we study such systems often? Well, we just time aggregate them, right? So we define a certain time slice, a window, and then all of the interactions that occur within that time slice we represent in the network model, because that's what we need, because we need to have some kind of connected structure so that we can say something based on network science methods. So why are we actually doing this? So the first thing is, this is a very nice and simple model that captures the direct interactions between the elements in the complex system, right? But even more important, and we sometimes actually forget that, what we actually get from a network model is we can also say something about indirect interactions, and that's actually in many ways a more important aspect, right? So here we see, for instance, that B and C are not directly connected, but what is implicitly included in the network model is that D and C can nevertheless indirectly influence each other via a path of length 2, for instance, via the node B. So it means we have transitive path in this network connection. So if you now go back to the time series data, you see that such a path also exists in time. So we call it a causal or time-respecting path. So it means here in the sequence, if something spreads from B to B, it can spread on from B to C the next time step. And that means there is an indirect influence from B via B to C. The problem is that just by reordering the links in this topology, we can actually break this property. So it means what we have now is we have a sequence where there's no way how D can indirectly influence C, but this sequence is still represented by the same system, by the same network type. Why? Because the number of interactions is exactly the same, the frequency of the interactions and also the interactions themselves. The only thing that I have done here is I have shuffled the interactions. Now what we see is that the ordering of these two interactions has been changed, and that means there's no way how D can indirectly influence C via this path, because something would have to travel backwards in time. So that's a complication that comes actually from the arrow of time, right? Because we can only move forward in time. So important observation from this, and that's basically the basic thing to understand what I'm going to present, is that whenever we use a network model of time series data, we discard information on the timing and the ordering of the links, right? That's an important observation. And what is even more, so we have done a couple of works on that, where we could show that if the temporal or timestamp link sequences contain specific types of temporal correlations, then we can actually break this transitivity of path that we implicitly assume whenever we use a network model. So that's actually important, and what we can also do is we can actually kind of put a price tag on that. So what we can do is we can quantify how much information, in terms of bits of information, is lost when we replace a timestamp sequence by a network model. In this case, this would tell us, okay, there's actually more information lost in the right example than in the left example, because there's a much more complicated path structure that's not captured by the network. But I'm not going to go into the technical details of that. Let me just answer the question, why is this important, right? Because why do we care about these temporal correlations? Why do we care about transitivity of path and information loss? Because at the end of the day, we want to relate the structure of a complex system to its function. And how do we do this? We do this by modeling dynamical processes. Right? So here's a simple dynamical process in physics. So we have a Euclidean space. That's a simple Higgs diffusion equation. And what we see is we just get the Laplacian operator, differential operator that describes the dynamics of this process. What is nice about the network view is that we can now discretize this space, kind of in the lattice topology. And then you see this Laplacian operator naturally becomes such a Laplacian matrix, which we can use to study the same process in this discrete topology. And if you think about it, one of the successes of network science has been the ability now to generalize this to arbitrary discrete topologies. So that means now we can interconnect things in arbitrary ways, encode this in a different Laplacian of the system, and now model the dynamical process on top of that. So it means we can calculate eigenvalues of this matrix, we can say something about stability of dynamical processes, relaxation dynamics, resilience, and so on and so forth. So that's certainly pretty cool. But now let's see how this holds up in real systems. So here's an example for a real system. So that's the network topology of the longitude natural network. And what I'm doing here is I'm using these equations actually to model a diffusion process in the system. Why? Well, there's no meaning of diffusion in the system. But what we are doing often is we are using this as a proxy to learn something about important nodes, about small cuts in the topology, efficiency of the system, resilience, and so on and so forth. That's how the process looks, and it's not very surprising. So you see there's kind of a flipping behavior that is due to the many cycles that are in the system. And then you see it takes rather a long time to move through the system because we have these long chains, so there's long path in the system. It's not very well connected from an algebraic point of view. So that's fine. Now we can say based on that something, for instance, about the most important nodes and so on and so forth. But there's a problem with that. That is related to what I said before, because what we should think about is that we make strong implicit assumptions whenever we apply such a model on a network topology. And a simple way to formalize this is that we can say that whenever we use graph theoretic and algebraic techniques, like for instance calculating these eigenvalues, we implicitly assume that the path in the system, paths of indirect interactions in the system are Markovian. So what does this mean? There's two ways to see that. The first one is, on a sequence of links that constitute a path, we implicitly assume that links are statistically independent. Or, from a Markovian, non-Markovian perspective, you could see it as the sequence of nodes traversed by a path are assumed to be generated by a Markovian stochastic process. That means the next step on the path only depends on the current one, based on the link, but not on the history of the path. That's an assumption that we make, and it's a pretty strong assumption. And what we can show is that temporal correlations in real systems lead to non-Markovian path. That means we break this assumption here, and that leads to completely different dynamics of processes of this. So now what I can show is the diffusion process in the real system, where we use the non-Markovian path that we can trace based on the schedule of real train connections and the ordering in which stations are connected, and that's how it looks. So you see we get a completely different view. And this is easy to understand because trains are moving in specific patterns and that moves the process much faster. So this may seem trivial, but it's something we should not forget whenever we apply network analysis to the network topology, because that's exactly the pattern that we don't take into account on our tools. Right? And what we could show is based on this, we are ignoring of non-Markovian path if we use just network analysis, we are getting actually wrong results. Sorry. No, it doesn't stop. Yeah. So we are getting wrong results not only on dynamical processes like diffusion or dynamic spreading, but we also get a misleading view of cluster structures in the system because paths are different, right? We get different node centralities and we get different, controllability of systems. So systems will be harder or easier to control based on these order correlations in the system. All right, so let me show you actually two examples. I'm not going to go into details of this because actually the first one I explained in much more detail actually 2 years ago when I gave a talk here as well. Let me just show you what can be the influence of these non-Markovian paths on dynamical processes in terms of numbers, not just vision. So we can actually quantify this as follows. So we take the temporal network sequence, Then what we can do is we can simulate the random walk process as a proxy for diffusion, and what we can study or calculate is actually the realization time for a given convergence threshold epsilon. So how fast does the visitation probabilities actually approach the stationary distribution of the system? So for instance, for this sequence, which is actually the empirical sequence that we get, you may find that it takes 200 steps. Okay. Now what we can do is we can shuffle the sequence and we can destroy this non-Markovian path and get Markovian path statistics because we have made independent path by shuffling that. And now what we get is, okay, now it may take only 100 steps. What we can take from that is we can divide these numbers and we can calculate for every point a slowdown factor, which tells us how the non-Markovian path influences the speed of diffusion in terms of a slowdown. Here it means it's 2 times slower than we would expect based on Markovian path assumption. Now we can do this for any epsilon, and we get these interesting curves here that tell us how non-Markovian path affect the process at different stages. And you see the epsilon 0 is basically the t to infinity limit. So we can look at actually the convergence of this to a certain slowdown factor, and that's what we can do. So that means now for every empirical system, we can plot such a curve and see what is the effect of ordering in the system on the dynamical process. So that's actually the result for 6 different systems. So first of all, we see that all of the curves, or many of the curves, actually look very different. It's interesting by itself, so it's a complex effect. And if you look at the value to which these systems converge, the slowdown factor to which they converge, you see they are first of all very different. And for 4 of the systems, you see that this ordering actually slows down the process, but for 2 of them, you see that it speeds up the process. That's actually something that is not intuitively easy to understand, because it is easy to understand why there is a slowdown, because as I said, the path transitivity that exists in the system, if you have a Markovian path, is broken. So that means not all of the paths that we expect to be there are actually there in the real sequence. So then it's easy to understand, okay, that should slow down the process. But we see interestingly that in some systems, this breaking of transitivity is in a specific way so that it actually nevertheless speeds up the process through the topology. That's interesting because it means that there is an interplay between the topology of the system and the timing of the links that can lead to both effects. So I'm not going to go into the details of that because I presented it already. I just want to add another perspective that is based on our most recent research, and that looks at controllability of the system. So now let's assume we have a linear dynamical system in the network, and we can also control some of the driver nodes in the system. And now we can ask how long does it take until we can control a certain fraction of nodes in the system. So that tells us actually how easy the system is to steer towards any state that we want to set. So again, I saved any equations. I have some backup slides if you're interested, but I think it's enough to say that we use the structural controllability framework and we apply it to this directed acyclic graph representation. And then what we can show is actually that we can map the controllability to a maximum flow problem in this graph structure. So what we can then do is, again, the same thing. So we take an empirical sequence, and then at a given point in time, we can calculate what fraction of the system or what fraction of the nodes can we control at this point in time. So that goes from 0 to 1. 1 would mean we can control all of the system, so we have full control of the system. Then we get a certain number. Now we can again shuffle these interactions and we get a different number. So here we make it larger. And now if we do this for all times in the evolution of the system until we can control the whole system, which is here always the case because we have a fully connected structure over time, then we get these curves that tell us how non-Markovian paths actually affect the evolution of control. And here in this example, you see that the ordering makes it harder to control the system. So we control the full system later than we would if paths were ordered actually in our. So again, these are the curves for the same six systems that I have shown before. A couple of observations again. So you see that there's a large variety of effect. And again, if you look at the order of these different colored curves, you see that in one case, the ordering of the system actually helps controllability, and in all of the other cases, it actually slows down controllability. So that's important from 2 angles. The first angle is that we can again have both effects depending on how the order correlations and the topology of the system kind of play together. And what is even more important is that in this particular case, where we see the speed up of diffusion, we see that the controllability is actually slowed down. So it means in the same system with the same temporal correlations, the temporal correlations can have opposite effects on different kinds of processes, which makes it important actually to understand why this is the case. So, and that was really the starting point also for us to see these complicated effects and to see how can we explain this and how can we address this also analytically. And for that, I would like to take a step back and rethink what we actually do when we make a network model of a complex system. So as I have said before, a network model is a graphical model that captures direct interactions that you observe between the elements of a complex system. Right? That's pretty much the definition. So it means in this example, again, with our two sequences, for instance, we have 12 interactions between A and B, because each of these interactions occurs 12 times, but in different orderings at different times. What is important to understand is that whenever we use such a network model, we are making implicitly a maximum entropy assumption about the path of longer indirect interactions. Because that means we have not put any information about real interaction path into the system, and we are replacing it by this Markovian assumption, which we can actually show is something like a maximum entropy ensemble of the path of indirect interactions in a complex system. That is all fine. Maximum entropy is great if you have no knowledge, because you make kind of the least mistake on average. But the point is, whenever we have time series information, we often can infer real paths. So that means we have information, and then we should ask, well, is it then justified to use a maximum entropy model? Or should we use the information that is in the data to get a better model for the path of the system? And that's exactly what we have been doing over the past 2-3 years, actually, to develop a framework that can do this. And it's actually pretty easy, because you can see it as a, let me just go back one slide, you can see it's just as a generalization of the standard network model, which captures the frequency of direct interactions. Direct interaction is a path in the system of length 1. So now we can see this just as a first order model for k equals 1, and we can just generalize this to, for instance, a second, a third, and fourth order model, where we make a network representation that captures the statistics of path of length k. And that's what we can do for a second order model, so that's k equals 2. So that means what we are doing is we're making a transformation of nodes to links. That's a link graph. It has a specific structure that is called a de Bruijn graph, which is also used in sequence modeling. Because what we are actually interested in is modeling of path sequences that we can infer from the data from a certain point of view. So what you see here is that we are linking two nodes that represent edges or links in the system by a link that captures the frequency of that particular path of length 2. It means ABC occurs 2 times, so we link the node edges AB and BC by a link with weight 2. That's exactly the same like the first order network, but moved to a second order representation, right? What is interesting now is if we apply this to the sequence, then you see if we calculate the same for the right sequence, which is exactly the same first order topology, we get a different second order topology. So now this part occurs 3 times, and what I have said before, that D is not indirectly interacting with C via B, is now visible by the absence of this link. So we see that what it does is it's a very simple graphical representation that nevertheless captures what we call the causal topology of the system, because it tells us actually which nodes can interact with each other via indirect path. And it captures more of this information than the first order network, because the first order network doesn't capture any of the order information. So specifically, second order models are cool because they are the simplest graphical models that still keep information both on the topology and on the ordering of links in the system. So the takeaway message here is that what we are getting essentially is a lossy representation of time series data that nevertheless captures the interplay between time and topology based on time series data, right? So obviously we discard information as well, because there may be higher correlation length in the system, which we don't represent here, but we represent more than in the first order. So we can make the model more complex, and then, basically capture more of the real interesting elements.
Can I ask you
Yeah.
a quick question? So the second order topology is just to me seems like a line graph. So
Yes.
where the line graph is just all the edges are now nodes and the nodes are now connecting. Okay.
That's actually the rule. So every de Bruijn graph of dimension n, or order k, is the line graph of the de Bruijn graph of k minus 1. So it means the second order model is the line graph of the first order model, and the third order model is the line graph of the second order model. So it means the third order would be A, B, C, and then actually B, C, D. And what is nice is actually this de Bruijn graph representation, we are always having an overlap of k minus 1 nodes on a path. So it means A, B, and B, C overlap in 1, because here we have k equals 2. This seems like a detail, but it's important because what we can then do is we can interpret walks in this graph as one step on a path, because with every walk we extend an existing path by exactly one step. Right? We just have a prefix that we discard. And that means that we can actually interpret this also in terms of matrix representations, and we can calculate eigenvalues and these kind of things and model dynamical processes in this, and get the same kind of representation or interpretation like for first order models. Alright, so that's exactly what we do. So in order to explain now this complex effect of ordering on controllability and diffusion, what we look at is a way to do spectral analysis of these causal topologies, and that's actually fairly easy. Because what we can do is now following, we take an actual sequence, we generate a second order topology as I have explained. At the same time, we can generate the first order topology, which discards all of the ordering information. Now from the first order topology, we can use this Markovian path assumption to generate a Markovian second order topology. Because an uncorrelated sequence we can still represent in the second order model, where all of the link weights of second order correspond exactly to our expectation if links were independent. And that's cool because now we can compare what we expect in second order to what we have in second order. And specifically, we can compare these topologies using spectral methods, for instance. For instance, we can calculate transition matrices. This is like the null model transition matrix. This is the real transition matrix. Now we can, for instance, calculate eigengaps of that. And what we can show is that we can understand the effect of ordering on the diffusion speed by looking at the difference between these two eigenvalues. And the same thing, so this is now basically one paper condensed to one slide, we can do for controllability. So that means because of structural controllability, we can understand this as a max flow in, along the causal path in a temporal network. And this max flow, we can calculate an upper bound for that based on the algebraic connectivity of the Laplacian of the system. So that means we can again calculate the null model Laplacian for the Markovian topology and compare it to the real one. And then we can look at these two values and understand the effect of ordering on controllability of systems. So actually very easy idea basically. But it works. So this is now some examples from the ones that I've shown before. This is the London tube system, and this is not a first order network, this is a second order network. So this is a visualization of kind of the causal topology. You kind of intuitively see here in the graphical representation what you have seen in the process before. Because what you see now is that every station is represented by two nodes, because in every station you can go in and out. And since we have a link graph, these are two nodes in the second order representation. And now you see these links in cross, and here you see the link weights are much thicker within one direction. So that means that's natural because trains travel in one direction, so it's much more likely actually to go in one direction than taking turns, basically. Yes?
What's the node? So nodes are stations. What's the node placement? Because I'm trying to make it look like the famous map of the one that I've run in my head, and I can't quite fit it.
I wonder, I think, so actually I have different representations. There's one where I used actually the physical location of the nodes. Because there's coding of London tube stations, but I think that's not that. I think that's just a Fokker 9 bot, in this case, of the second order topology. And what we are doing is actually we're using the same layout for both so that we actually see what maps to what. Or is that what you asked?
Well, I know, you know when you go and you visit London and you're in tourist, you get the little fold-out map?
Oh yeah, yeah.
Yes, and it's a representation that's not purely correct geographically.
Yeah,
I'm
I
trying to
think
map this
also not
onto that.
geographic. That's not geographic.
Right,
Yeah.
that would help, maybe.
I have one, yes, but I have not in the slides. But it's a bit more convoluted, the geographic one. So because also, I mean, the longitude map is not geographic for that reason, right? So this also not maps to the usual logical maps that you get, if that's what you're asking. It's a forced direct layout. All right, but anyway, what you see is that there's differences in the second order topology easily explained by the dynamics that we have seen. And now we can understand the effect on the process by looking at the eigenvalue gap of the second order transition matrix. So you see here, the eigenvalue gap is larger, which means that the process is actually faster. If we look at control, what we can also do is we can calculate the precise speed up that we see in the data by taking actually the ratio of those, because that tells us actually the diffusion speed ratio. So we can even make analytical arguments about the process, which is a nice feature. So it means in this case it would mean the process here, the diffusion process, 4 times faster. So if you look at controllability, then we can understand the speed up effect also by looking at the algebraic connectivity of the system, which you see here is by a factor of 10 larger. So that makes it easier to control the system. Another example, these are contact sequences of staff at a hospital from the social patterns collaboration. And what we observe here is that diffusion is much slower in the real sequence than what we would expect at random. That's something we can understand based on a smaller eigenvalue gap. We can calculate again the factors, so here it's almost 6, 5.75, which matches actually what we see in the data. And in terms of controllability, you also see that we have a much smaller algebraic connectivity, which explains why it is harder to control the system. But the last example shows that these two things are not necessarily coupled, because the ordering can have more complicated patterns. So here, in this example, these are flight paths in the US, so these nodes are basically in the second order network are links between inputs. If you look at the actual second order topology, we see that the eigenvalue gap is actually larger, so it means that there is a speed up of diffusion. But if you look at the algebraic connectivity, it is actually smaller. So it means there is a complicated pattern which changes path structures in terms of maximum flow becoming harder, or actually less, and diffusion becoming faster. And this complicated pattern that we see based on the simulations, we can understand based on these higher order models. All right, so higher order models are cool. They're useful to understand diffusion. We can also look at validity spreading. We can understand better controllability of systems with dynamic topologies. We can also apply actually community detection, because now we can detect communities by taking into account ordering of links. And we can improve node centralities and information retrieval. I will come to this in a moment. Also, we can develop cool new network visualizations. I can show this if you're interested, but I would skip it for now. So that's fine, except for that there is an elephant in the room. That's actually the title of my talk, because I was talking about optimal models of complex systems. And now let's actually critically think what I talked about in terms of higher order models. Because from a certain perspective, what I'm saying is kind of trivial. Because if we generate higher order models of time series data, what we are doing is we are kind of shoveling information from the data into the model. So we should expect that this model better captures the dynamics that we see in the real system. Right? So it's a classical machine learning overfitting question. So the question is now, which order of a representation is justified to study a given system? That's a hard question. And that's actually what I was interested in most recently, and that's actually a recently published paper. So what is the optimal order to model a given system based on this higher order framework? And if we are able to answer that, we can also answer the crucial question, which is, when is a standard network model justified? Because if this optimal order is 1, that tells us that there is nothing in the data that would deviate from the assumptions that we make when we use a network model to study the system. Right? So these two questions are a bit harder to answer, but I think I have a way to do this, and I want to discuss it. So the basic idea is that we can generalize, again, higher order models to something that I call multi-order models, multi-order graphical models. And the idea is the following, or let's say the problem is the following. A second order model captures correlations of a specific length, of length 2, in the sequence of events. Right? So it's a higher order Markov chain model in the sense that it has a memory length of step 1. Basically. If we do a third order model, we can only capture correlations of length 3. If we do a fourth order model, and so on and so forth. So that means every of these higher order models captures somehow one slice of correlation length that exists in the system. And that makes it a bit hard to compare them, to say what is actually best to model the system. To fix this problem, I was thinking the following: why don't we combine multiple of these higher order representations to a multi-layer graph model, right? So the idea is we can just generalize it again. So a multi-order model with a maximum order of 1 is just a network, right? And now we can make this a 2-layer model where we add on top of that a second order topology. So it means the first layer of the system models the system topology, and any layers larger than 1, they capture these non-Markovian characteristics of the path that we may observe in the system. So it means we can add the second order layer, and on top of that, we can add a third order layer, and so on and so forth, up to the point where we stop this. And what we do implicitly then is that we assume that paths are transitive and Markovian that are longer than the maximum order of our system. So that means that there is no memory longer than the maximum order that we have. Right? So the nice thing is that now we get a graphical model which we can interpret as a stochastic generative model for path that we observe in time series. And what this means is that now we can actually recast our original question, what is the optimal order to study a system, into the question of how many layers of these models do we need to explain the path that we observe in time series data. Right? For instance, causal or time respecting path in time-stamp matches. So, basic idea would be the following: we just calculate the likelihood of this generative model given the path that we observe, which is very easy, because for every path we calculate how easy is it, how likely is it to generate that, and then we compare them, which is obviously nonsensical, because as we add more and more layers, the likelihood obviously of the model increases, up to the point where if we have actually all of the layers up to the maximum length of the path, we can always almost perfectly reproduce the path that we observe. So that is the point where we're just overfitting the system. So yeah.
So the explanation of a path is within one layer, or can it move from one layer to
It
another?
moves across. So the way I'm doing it is actually, if I observe a path from Tina to Ingo to Carolina to Tim, and so on and so forth, then actually what I would do is actually for this path, I start in zero order layer, because at the first step, I have no memory. There's no way to have memory. Actually, it's a bit more complicated than what I showed here, because, and actually also a bit more interesting if you think about it, because I also have a zero order layer.
Yes.
Which captures the mean field model, which also means we can do model selection to see whether we even need a network or whether mean field model is enough, but I'm leaving this out. That means the first step, I draw in a zero order model, and then I move step by step up until I reach the maximum order, and then actually I generate path statistics in the maximum order layer, because that's where I assume Markovian statistics. So with this simple process, we can actually calculate the likelihood based on any path sequence that we observe.
Do you assume there's a cost going from one layer to the next, or there's no cost?
Cost in terms of?
In terms of like number of bits that you need to store?
Yes, yeah, that's coming up.
Okay.
Because that's what I said, it's trivial that with more layers you
Yes.
get better explanatory power. That's actually the really hard part. And that's also how it actually deviates from standard Markov polynomial. I will come to that.
For the models,
Because,
for the model selection, you penalize for each layer, right?
yes.
But is it possible, like certain fraction of the nodes, that you only need 2 layers, but the rest of the network you might have 4 layers, so it's kind of like mixed order?
That is an interesting question. We haven't looked at this yet, but we think it is the case in many systems. So you could do this in different ways. So you could make information theoretic arguments on the top layer and say, well, actually, we can actually lump 2 states together, and then we calculate how much information we lose about the real path. And then beyond a certain criterion, we just aggregate them, and then you can reduce the model layers. Or you could try to generalize variable order Markov techniques, but that's what I tried. Is actually, I haven't found a way. But you're right. In reality, that's what we would have. The framework cannot do this yet. So what we get right now is we get a optimal order for the whole system that assumes that actually this is the best compromise for all of the paths of all of the nodes. Okay, so now how can we account for this complexity, right, that we add? That's now the crucial point. And why actually I think these multi-order models, these multi-layer models are interesting is because they are nested models. So it means the model MK is a special case of MK plus 1 because we can have just the third layer, the Markovian statistics, which gives the same like a second one. And this nestedness properties now translates to something beautiful mathematically because we can apply the Wilks theorem to make a likelihood ratio test where we know that likelihood ratio converges to a chi-square distribution, which we can calculate based on the difference in the model complexity between the model with 2 and 3 layers, for instance. And the only thing we need to do is to calculate here the degrees of freedom or the complexity of a multi-order model with maximum order k, which we can actually easily do. I'm not going to show the formula now. If you're interested, I can show it later. But the point is we can put in the complexity of these models into the testing procedure. What we are getting then is we can analytically calculate the p-value of the null hypothesis that we need k layers against the alternative hypothesis that we need 1 layer more to explain the data. So, and that allows us now to kind of iteratively calculate the optimal maximum order k. So this is a bit more technical, so let's make a visual argument about this. So how can we use this to answer the question when a network is actually a network? So let us visualize this as a scale where on the one side you have the data that you want to explain, and on the other hand you have the model with which you want to explain the data. So if the only information about the system that we have is the link topology and nothing more, then a network model is obviously justified because we are making this maximum entropy assumption of path, which is justified if we have no information on the path. Right? But if we have time series data, what we can do now is based on this model, we can calculate the explanatory power in terms of likelihood for the data that we observe. And we can actually calculate the complexity of this model of order 1. And now we can contrast this with a model where we add the second layer that is more complex, but that explains the data better. And with this likelihood ratio test now, we can assign a p-value whether the increase of complexity is justified given the increase of explanatory power. So with this, we kind of automatically balance complexity and explanatory power. And then at some point, when we add the third layer, we will find, okay, this is not justified anymore because now it's likely that we just see the increase of explanatory power because we have made the model much more complex. So it means it automatically accounts or penalizes the model complexity in this way. And with this, we can then tell what is the optimal order to represent the system. So one way to see this is that it automatically kind of is a compromise between actually Occam's razor. So that means we should not make the model more complex than necessary. And this quote of Albert Einstein that we should not use models that are too simple to explain reality, right? Because that's what we test in terms of explanatory power. So, or to put it in plain machine learning terms, we neither want to overfit and we neither want to underfit. So that means we avoid too complex models and we avoid using network models when actually task statistics do not justify. So the takeaway message is that we have a principled method to determine not only when a network model is justified, but also which and at which order. So, last content slide, if there's time. So I can tell you a lot that this is a principled method, it uses statistical techniques, that's all fine, but what does it actually tell, right? So can we actually cross-validate this in terms of predictive power? And it turns out we can. So what we did is the following. I used time series data on different technical and social systems where we have time-stamped interactions. And what we can do now is we can assess how well does a model that we learn with this method allow us to predict something about the importance of nodes that we can measure as ground truth in the data set. So the way we do this actually in the sequence, we can calculate visitation frequencies that give us a ground truth node importance. And then we can try to estimate this using PageRank on the topology, and we see how well it kind of the topology predicts the real importance. We can do this now in different orders of the representation. And this plot is already striking because this is actually the prediction quality, so how well our prediction corresponds to ground truth. For instance, for the social contact network, it could actually almost not be worse because it's basically uncorrelated. So it means the network topology doesn't say anything about the importance of actors in the social network. For the transportation network, it's also bad, but you see at the same time for the email communication network that we have here, the network, first order network is actually the one. So now what we can do for every order that we add to the system, we can calculate this prediction quality. So actually this is the case where it's a good and a bad model. And now we look how it looks for different orders. And what you see here now is that indeed for the social network, the prediction quality increases a lot if we add higher order layers. For the transportation network as well, with a different curve. And for the communication network, indeed the first one is the best representation. And the circled ones here are the points that are detected by our framework. And what you see is that really the order that we detect with our method is also the one that has the highest predictive power about the data. So it means it captures actually a real pattern and it's really not overfitting, right? So that means, as a takeaway message, what this multi-order model framework gives you, it kind of gives, you can see it as an optimal compression of the causal topologies of real systems based on time series data. So that's really what it actually does. So now let me conclude why I think that this gives new perspectives for data science. If you think about it, and I like to think about this from a philosophical, historical point of view, how we came actually to network science, right? And the point where we are interested in complex systems and to model the interactions between elements, and we had no idea of the topology of these interactions, we would resort to mean field models, right? We are just averaging the interactions in a mean field. But then there may be systems where we have more information about the interaction topology. For instance, it's a physical system, so we have a lattice topology, or we know some statistics of the interaction, so we can use random graph models, or we know the precise topology, so we use complex network models. That's great because we have kind of stepped up our abilities to include topological information about complex systems in data-driven modeling, right? And we're kind of here. So the point is what this neglects, that there is kind of an orthogonal temporal information, temporal dimension of complexity that we actually discard by just looking at the topology. Because we see that because of the interaction between these two dimensions, the real topologies of systems can be much more complex than what we would expect just based on the network model. So and what we also see is that real technical, social, and biological systems, they live up here. So they are complex from a topological point of view, but they are also in many cases complex from a temporal point of view. And this kind of range we cannot really cover with standard first-order network models, right? So what we need is actually multi-order models that capture both topology information and time information in the graphical representation. And that's kind of cool because now we can use our network science expertise on these models. And we can calculate centralities, we can model dynamical processes, and so on and so forth, on these more complex models. So let me just conclude that there is a software implementation of this whole framework, so that's out on Python, GitHub in Python. It supports out-of-the-box data on temporal networks, so timestamp links, sequential data, so if you have pathways, click streams, something like that, and also direct acyclic graphs if you have like more complex path structures in the system. And it implements also this model selection, higher order centrality measures, the spectral analysis that I have shown, and also clustering techniques. An educational tutorial, and I think that's a way how we can turn complex time series data actually into optimal network models. And now I'm happy to discuss with you. Thank you very much.